From theCUBE studios in Palo Alto and Boston, bringing you data-driven insights from theCUBE and ETR. This is Breaking Analysis with Dave Vellante.
We believe the industry's broad interpretation of Jensen's law, i.e. Jensen's law is really just an acceleration of Moore's law, misses a fundamental economic reality of AI factories. Our analysis indicates that Jensen Huang's own language and NVIDIA's operating model point to a financial law of motion for AI factories. When power is the key constraint, investments that increase performance per watt and cluster efficiency raise monetizable throughput faster than they raise total costs. The result is a new law for the AI era, what we see as the real or the true Jensen's law. Specifically, spend more to make more, i.e. revenue goes up, and spend more to save more, i.e. unit cost goes down. Moreover, there is a corollary in this new regime in that fabric-driven utilization unlocks are so valuable that high-speed networking becomes essentially free. And in this breaking analysis, we explain in detail what we're calling the real Jensen's law. We'll explore why this phenomenon is so important. We'll review the math behind this new Jensen's law, or our interpretation of Jensen's law. We'll share some concrete examples of where the law is applicable and when the corollary of the network is free holds. And we'll talk about implications for investors and operators and where the law is not applicable. Now, why is this important and why now? But we're moving beyond single-shot prompts where reasoning and agentic AI multiplies compute per task an estimated 100 to 1,000x. This is according to Nvidia. The data centers are increasingly power capped. So when you think about Nvidia's GB300, NVLink 72, Spectrum X stack explicitly, it targets tokens per watt as the metric to optimize along with achieved utilization. Together, these two variables directly allow customers to monetize power-limited factories. AI factories, that is. Let's look at some of the supporting statements from NVIDIA's Q2 FY26 call, which took place on August 27th. The core of Jensen's law, as we define it, is simple. Performance per watt drives revenue. In a power-limited data center, the number of tokens that you can produce in a year is directly tied to how efficient you are. Or, as Jensen put it, perf per watt drives directly to revenues. The more you buy, the more you grow. And on the call, NVIDIA cited massive efficiency gains, 10 to 50 times more energy efficiency with GB300 versus Hopper, depending on configuration, and the use of FP floating point 4 precision and NVLink 72. We also got a concrete ROI proof point. NVIDIA claims $3 million in spend on a GB200 infrastructure generated $30 million in token revenue. That's a 10x return. Presumably, this is not a model, but actual operating data from the likes of Microsoft and OpenAI. They didn't cite that specifically, that's our inference. And networking is playing a much bigger role. By lifting utilization from around 65% toward 85 or 90%, the company argues that networking is effectively free because the throughput gain more than covers the fabric costs. Now, the stack itself spans all three dimensions: NVLink for scale up inside the rack, Spectrum X, Ethernet, and InfiniBand for scale out and across clusters, and Spectrum XGS for scale across multi-site AI factories, something we just wrote about last week and published in theCUBE research.com. So you put all this in the context with spending. NVIDIA claims hyperscalers are on pace to spend about $600 billion a year on data centers, a figure, by the way, that we pegged a couple weeks ago lower at just north of 400 billion, but I mean, we just wrote about this today. Nonetheless, this is still huge and growing. Moreover, NVIDIA sizes the remaining decade's AI infrastructure build at 3 to 4 trillion. This is the CapEx flywheel that Jensen is pointing to. And by the way, our estimates are somewhat lower than that, probably in the 2 to 2.8 billion, so pretty close. Anyway, maybe Jensen knows something that we don't know. So reframing Jensen's law is what we're trying to do here today, and we're moving from faster chips to factory economics. So the common usage in the press, and this was first produced by IEEE Spectrum, they kind of coined the term Jensen's law. The Wall Street Journal picked up on it, and other publications like Tom's Hardware have written about it. They position Jensen's law as Nvidia's acceleration beyond Moore's law, like Moore's law on steroids. So shorter cycles and outside generation over generation gains. So Moore's law is every 2 years, Jensen's law every 1 year, as they've defined it. And that's directionally spot on in our view, but it's incomplete because what it misses, we think, is the lever of economics. So our premise today is there is a version of Jensen's law that is more than just marketing hype, and it relates to the economics of AI factories. So let's review and talk about the core principles that are emerging in the economics of AI factories. In a power-limited environment, every incremental dollar of spend that improves performance per watt and fabric efficiency drives monetizable throughput. That's the premise that we're taking away from Jensen's statement. And so that's tokens per second. So it drives token per second, all this faster than it raises total costs. So that dynamic leads to two outcomes. One, spend more, make more, meaning revenue goes up. And then the second is spend more, save more, meaning unit costs go down. And here's where it gets interesting and what's new. When utilization gains at the fabric level are significant, high-speed networking becomes essentially, the company claims, free. So the point being there that the throughput lift outweighs the amortized cost of the networking gear. And this framing ties directly back to some of the classic laws of technology economics as shown on the right-hand side of this graphic. But what's new here is that these principles are being operationalized specifically for power-limited AI factories. And we're anchoring them with explicit revenue math, which we're going to share shortly. So that's the shift, moving from abstract laws of progress to concrete financial drivers of the AI economy. So let's take a minute. It might be helpful to review these classical laws, and then we'll tie them into our new interpretation of Jensen's law. So Moore's law, as you know, speaks to device scaling and feeds the performance per watt gains, i.e. the more tokens you can produce per year at a fixed power envelope, the better the economics. Wright's law, which, Kathy Wood says her core research is based upon, and of course David Floyer and I always talk about Wright's law, but it's not widely cited, but it's important. It speaks to cost declines as cumulative volume doubles, and this explains the cost per token falling as deployment scale, which is core to the save more side of the equation. And then, of course, my former colleague from IDG, Metcalfe's law, value grows exponentially as a function of connectivity, and this talks to network utilization, the scale up, scale out, and scale across, making networking effectively free. Then, of course, Jevons paradox, which became really in the mainstream, made more popular by Satya Nadella's commentary post the DeepSeek introduction of its large language model that freaked everybody out. But Jevons paradox essentially talks to efficiency increases and consumption, and basically says as costs go down, people buy more. And so that supports the flywheel effects of Jensen's law as we've redefined it. Okay, so what's the math behind all this? Let's break it down behind what we're calling the real or the true Jensen's law. So we can boil it down to three things: how many tokens you can generate, how much revenue those tokens produce, and what each token costs to make. So start with throughput. Tokens per year. That's a function of four variables: the power budget, the amount of operating time in a year, the overall efficiency of the system, meaning tokens per unit of energy, and how well you can utilize the cluster. You put those together and the formula goes as follows: tokens per year equals power times efficiency times utilization. Once you know throughput, revenue is just a matter of multiplying tokens by dollars per token. So that gives you the top line. Now let's look at the cost side of the equation. So cost per token is your total annualized expense. So we're talking servers, racks, networking, cooling, electricity, staff, real estate, and you divide that by tokens per year. In other words, take CapEx plus energy plus other OpEx and spread it across your token output. And then finally, that leads us to gross margin. That's 1 minus the cost per token over the price per token. So put simply, the more efficient you are at generating tokens and keeping the system utilized, the more your margin expands. So when we say performance per watt times utilization equals revenue, that's the math. It's not just a marketing slogan, it's a financial model for AI factories. But in the words of Mona Lisa Vito, there's more. The accretive spend rule, in other words, the importance of networking, is what we're talking about there. Here's the heart of it. If you spend more on a faster fabric, better cooling, or smarter software, and it improves efficiency or utilization enough, then the extra revenue from more tokens will outweigh the extra cost of that upgrade. So if efficiency and utilization gains are greater than the added costs, spend more, make more applies, because cost per token also falls, leading to spend more, save more. And then you have the Jevons style component. There's an unlock there, another amplifier, and that's the kicker. When efficiency cuts unit cost, you can charge less per token. And if your demand is elastic, customers want more when it's cheaper, revenue grows even faster, which reinforces the Jensen flywheel and Jevons paradox, as we discussed earlier. So let's break this down and put this in a picture and look at the value flow of Jensen's law as we've defined it, i.e. follow the money. In fact, let's put this in plain language. So think of the AI factory. Imagine it's a cafeteria, and the cafeteria has ovens. Let's call those the GPUs. It's got hooks that do the work, that's the software, and then it's got a delivery system, which is the network. The whole point is to serve as many meals, tokens, as possible every day, while keeping your cost as low as possible so you can make money. So here's the flow shown in this chart. Throughput is tokens per year. That's like the total number of meals that you can serve in a year out of your cafeteria. You get more ovens, you're going to cook faster, and it's going to have smoother operations, and that means more meals. Then take power times efficiency times utilization. That's just a fancy way of saying how much energy you put in and how long you run the cafeteria, how long it's open, how long the lights are on, how good the ovens are, how busy you keep them. So if the ovens sit idle, the factory, the cafeteria in this case, or the AI factory, this metaphor, is underutilized. And then there's cost per token. Every meal has a unit cost. There's ovens, which are a CapEx. There's electricity, which is energy. There's staff and supplies. That's your operating expense. You divide that by the number of meals served, and you get a cost per meal, which represents the cost per token. And that leads to revenue. If you charge money for each meal, which of course you do, then revenue is simply how many meals you can sell times the price per meal. This is the same for tokens. That leads to gross margin. This is the profit that's left over after the cost. So the lower the cost per token, the higher the number of tokens sold, and the more money that you keep. So Jensen's law is just this: spend more to upgrade the cafeteria, and you'll either serve more meals, make more, or you'll serve each meal cheaper. You'll save more. Now, if both happens, your profit gets a double whammy. And then networking fits right in. Better networking is like upgrading the cafeteria's conveyor belt, so every oven stays busy. Even if the conveyor belt costs extra, it, in theory, pays for itself because the cafeteria serves more meals. That's why Nvidia says the network is essentially free. Now, the loop on the right is the accretive spend rule. It means if you spend more, extra CapEx, better fabric, smarter software, and it increases efficiency or utilization enough, then revenue grows faster than cost. And the result is higher throughput, more revenue, and often lower unit costs. So the test is, does the revenue lift from higher efficiency and utilization outweigh the added cost of the upgrade? If the answer is yes, the spend is accretive, i.e. it's profitable. If no, then you've spent money without improving the economics. And the key is you have to take a systems view, which is something that Jensen always stresses, i.e., he says we don't just build chips, we build systems. And this is a key part of NVIDIA's moat, which is often underappreciated. If one part of the system is optimized, e.g. more ovens create more meals, but the conveyor belt is not as fast and can't keep up, then the system is out of balance and revenue is not maximized. So in the call, NVIDIA talked to real-world use cases that prove out our version of Jensen's law. Again, this assumes balanced systems and some other things that we'll talk about in a moment when our version of Jensen's law doesn't hold. But their Q2 results included some really strong proof points for our interpretation of Jensen's law. The company gave several examples showing how new architectures and fabrics translate directly into revenue, multiples, and lower costs per token. So here's our take on some of those that we're showing here. First, reasoning and agentic. Unlike simple chatbots with single shot, Jensen mentioned this a number of times on the call, these agents plan, they use tools, they talk to other agents, and they iterate, they think, and that makes workloads 100 to 1,000 times more compute intensive, which means efficiency and utilization gains matter a lot more. The second is GB300 with NVLink 72 at rack scale delivers, according to NVIDIA, about 10x the tokens per watt compared to Hopper, and that's with the 4-bit floating point math. It all combined with energy efficiency improves up to 50x per token. CoreWeave was the example given. Supposedly, they're already seeing 10x better inference on reasoning in production. And then the third is the fabric story. Networking isn't a side note, it's fundamental to the economics. Spectrum X Ethernet is something we wrote about last week, is already running at a $10 billion run rate. And that, an NVLink 72 is going to give you 14x the bandwidth of PCIe Gen 5, according to the company. So PCIe Gen 5 is off the shelf. Spectrum X Ethernet is purpose-built. Again, we wrote about this last week. That's kind of NVIDIA's claim. And that's kind of their counterclaim to the lock-in and you're not using standards. Anyway, this is why Jensen says the network is effectively free, because if utilization gains outweigh the cost, it is essentially free. The fourth piece here is the $3 million to $30 million example that Jensen cited, which is a real case where $3 million spent on infrastructure produced $30 million in token revenue. That's the spend more, make more flywheel in action. And finally, cadence. Because NVIDIA is shipping new architectures every year versus every other year, which is Moore's Law, Blackwell to Rubin and beyond, each one drives higher performance per watt, higher utilization, and higher revenue. So you have this compounding economics. And the bottom line is NVIDIA, they're not just selling chips, they're proving the economic engine of our version of Jensen's law. Heavier workloads drive the value of efficiency improvements, higher fabrics keep the GPUs busy, and each architecture flip compounds the spend more, make more cycle. So let's look at the investor lens and what Jensen's law, as we've interpreted, changes. So from an investor perspective, there's really four things. First is the unit of competitiveness is no longer the chip. It's the AI factory. So what matters is system-level performance per watt and utilization, which rewards rack-scale designs, integrated fabrics, and software, and the cadence that we just talked about, the annual cadence. The second point, networking isn't just overhead. It should be a profit driver. So utilization gains are so significant that fabric can routinely pay for itself, often multiple times over. The third is pricing power is being redefined by elasticity. As costs per token go down, providers can still grow revenue by lowering prices because demand expands even faster. We've seen this throughout the history of technology. Lower cost PCs, lower cost internet, lower cost cloud, on and on and on. We're already seeing this in the scramble for capacity and the shift to reasoning workloads. And fourth, cadence is a cash machine. What do we mean by that? NVIDIA's product cadence isn't just about faster chips, it's about turning capital spending into a recurring monetization flywheel for customers. Each year, new architectures deliver higher efficiency, more tokens per watt, and better utilization, which keep clusters busier. So this combination means that every dollar of CapEx spent on GPUs, networking, and racks generates more revenue in the following cycle. And this is what Jensen means when he says the more you buy, the more you grow. Customers that continually invest or reinvest, they ride that curve of annual improvements, that learning curve and that cost curve and that revenue curve, effectively compounding returns with each generation. Now, what about the operator view? How do we think operators are going to measure Jensen's law in the field? Here's what we think. Here's how we think they're going to measure it. First, tokens per joule. True efficiency is rising fast, 10 to 50 times in some cases. The other metric is going to be utilization. Operators claim that clusters run 15 to 25% more efficiently with NVLink 72 and Spectrum X. Third, power allocation. When the megawatt cap can be flattened or can stay flat, every gain in performance per watt just drops straight to revenue. Fourth, token price and demand. As prices fall, demand rises, and so does revenue. That's Jevons paradox. And fifth, payback time. So, some builds now recover inside of a year. And finally, what's the mix of fabric? NVLink 72 domains are scaling, and XGS is that data center to data center, AI factory to AI factory, scale across. That's just starting to emerge. And as we see, denser connections, that's going to compound. Now, there are caveats. There are risks and there are falsifiers in places when our version of Jensen law doesn't hold. So let's be clear. It is not guaranteed. There are conditions where it doesn't apply. What are they? First, if a data center isn't power limited, then performance per watt isn't as tightly tied to revenue. Second, if token prices fall faster than efficiency and utilization gains, then growth stalls, especially if demand is not elastic. Third, workloads make a difference. If the model isn't sensitive to fabric speed or collective operations, then the return on fabric spend is going to be less, and it may be negative. Fourth, practical constraints like supply chain delays, power, cooling bottlenecks that can push out the payoff, and that's real challenging for data center operators today, actually just getting up and running. Fifth, if alternative stacks or ASICs start to match Nvidia's end-to-end efficiency, the economics are good, but Nvidia's advantage will begin to moderate. Now, finally, this interpretation of Jensen's law works well for hyperscalers and consumer internet companies. Those are the big buyers right now. We've said this is like a one-lane highway that's really, really busy. It's crowded with a bunch of hyperscalers. It's unclear how well all this translates to enterprise AI, which, as we've reported, is in its nascent stage. Customers are building out on-prem AI stacks, but it's taking time, and the skill sets aren't necessarily there. And we'll see if it translates at scale the same way it does from hyperscalers. It's unlikely it will at that scale. And same thing for edge customers. And we're going to dig into that as those markets evolve. So those are the stress points that you need to watch. So in conclusion, hopefully our reframing of Jensen law, made sense and is accomplished. I mean, the popular sort of notion in the industry of Jensen's law is just Moore's law on steroids is necessary in our view, but it's insufficient to understand the economics of AI. The deeper analysis goes into those economics, which say in power-limited AI factories, efficiency, i.e. how many tokens you get per unit of energy, and utilization, how busy you can keep the cluster, are the real revenue levers. Improve those faster than costs go up, and both dynamics hold, i.e. spend more to save more and spend more to make more and spend more to save more. And this premise is backed in the latest and previous earnings calls from Nvidia, and they are providing hard evidence, 10x to 50x energy efficiency gains, 3 million infrastructure spend generating 30 million in token revenue, and fabric-driven utilization unlocking that effectively makes networking free. So the actionable items for investors and operators is they should evaluate vendors by factory economics, not chip specs alone. And the winners will be those who compound efficiency and utilization gains year after year. They get on that curve, they get on that learning curve. They are going to be out in front, and they are going to be the most profitable. Invest in those companies. And combine that with software and networking fabrics, doing a lot of the heavy lifting as much as the silicon itself. All right, that's it for now. Thanks to Alex Meyerson, who's on production and manages our podcast, and Ken Schiffman as well. Kristen Martin and Cheryl Knight help get the word out on social media and in our newsletters, and Rob Hoth is our EIC over at SiliconANGLE. Thank you all. Remember, all these episodes are available as podcasts wherever you listen. All you got to do is search Breaking Analysis Podcast. I publish each week on thecuberesearch.com and siliconangle.com. And you can email me at david.vellante@siliconangle.com or DM me at dvellante or comment on our LinkedIn post. And by the way, check out ETR.ai. We didn't use any of their data for this session, but they get the best survey data in the enterprise tech business. This is Dave Vellante for theCUBE Research Insights, powered by ETR. Thanks for watching, everybody, and we'll see you next time on Breaking Analysis.